So, we will discuss second law of thermodynamics today. Of course, since it is not a course on thermodynamics, we will not have a full proper discussion on second law. We will just have just brief discussion in the form of recapitulation. Now, second law of thermodynamics is very important physical law. See, the first law that express the conservation of energy, or in a change what type of change the energy will experience, but it does not say whether a particular physical process is possible or not. It simply says that in a physical process the energy will be conserved, the heat added to the system and work done on the system will increase the energy of the system. But there is nothing in this law which clearly say whether a particular physical process is possible or not, and the second law exactly does that. That is, second law tells us whether a particular process will be possible or not. The second law of thermodynamics are expressed in some classical statements, but exactly in those classical forms they will not be very useful to us. So, we will try to get the expressions that are directly useful to us. This indicates the possibility of a process or decides the possibility of a process, and in doing so it brings in the concept of a new state variable known as entropy. As the first law brings in the concept of internal energy, similarly the second law brings in the concept of entropy. It also provides a mean to define absolute scale of temperature. That is, that the zeroth law brought in the concept of temperature. However, the actual measure of absolute scale temperature is given by the second law. As we mentioned that there are several classical statements of second law. There are several classical statements of second law, and the several classical statements, and the most important of them are Kelvin Planck statement, and Clausius-Clapeyron or Clausius statement now Kelvin-Planck statement said that it is impossible for a heat engine to produce net work working in a complete cycle if it exchanges heat only with bodies at a single fixed temperature. It is impossible for a heat engine to produce net work working in a complete cycle if it exchanges heat only with bodies at a single fixed temperature. That is what is the Kelvin-Planck statement, and similarly the Clausius-Clapeyron statement says that it is impossible to construct a device which operating in a cycle will produce no other effect than the transfer of heat from a cooler body to a hotter body. Let us repeat the Clausius statement once again, that it is impossible to construct a device which operates in a cycle and produces no effect other than the transfer of heat from a cooler to a hotter body. Now, as you said that these classical statements are not directly useful in our context, and of course, from these classical statements we can obtain the useful statements or useful form of the law which are of direct use to us, but that is a subject matter of a full course on thermodynamics, and here we will not go in that approach, rather we will straightway get what it says. Now, let us think about any change and again come back to our indicator diagram. We know in the indicator diagram, let us say that indicator diagram P and V or 1 by rho, any point represents a state, and so if we consider any line that represents a succession of change. Now, of course, we can draw lines which defines the direction of a small reversible change, and also we can define lines which gives small reversible change without gain or loss on heat. So, let us say that this as an example, let us think about a line. So, this line represents small reversible change without gain or loss in heat. Let us say this is what is defined from this point. Now, of course, it is possible to define such line from each point and get a family of these lines. So, line drawn from each point will give us a family of such lines, and these lines are of course called adiabats. These lines are called adiabats. Because they represent adiabatic reversible change. Now, if we define then say again from this point goes on like this, and consequently we have, if we define from each point, of course, we will have a family of such lines. And so on. Now, on these lines the changes represents a reversible change. If we think about changes in succession, every time a small change, very slow change, then these lines can be regarded to define equal value of some new function of state. So, these lines can be, or this family of adiabates can be regarded to define equal value of some new state variable. And the second function discuss the property of this, the second law discuss the property of this function. Now, second law implies the existence of this property second law implies the existence of this property existence of this function and defines its property. This this state variable or state function is called entropy. Entropy is of course an extensive property that it depends on the mass, but we can have a specific entropy. The specific entropy which is intensive property an extensive property and the intensive property, that is specific entropy or entropy per unit mass, will let us denote it now by S. So, the second law actually tells us that those family of adiabates are lines on which this entropy is constant. So, the reversible adiabatic, those lines, as you have seen, that those particular adiabates represents reversible change. So, it says that in a reversible adiabatic change, entropy remain constant. So, it says that in reversible adiabatic change, entropy remain constant. Now, any process in which the entropy remains constant is isentropic process. The process in which there are no heat transfer and the processes are reversible, those processes are called isentropic processes. And with the help of this, the second law can be expressed also in this form, that in a reversible transition from one equilibrium state to another equilibrium state, the increase in entropy is proportional to the heat given to the fluid. So, another statement, or rather in a more useful form. So, another statement of of course, as we mentioned before, that this statement can be obtained from those classical statements due to Kelvin, Planck and Clausius. This says that in a reversible transition from one equilibrium state to another, that is, let us write, in a reversible transition from one equilibrium state to another, in a reversible transition from one equilibrium state to another, the change in entropy is proportional to heat given to the system and the constant of proportionality is also a state function, and the constant of proportionality is also a state function that depends only on temperature. What it says that if there is a reversible transition from one equilibrium state to another, then the change in entropy will be proportional to the heat given to the system. If no heat is given, the entropy will not change, and the constant of proportionality is also a state function and it depends only on temperature. And the inverse or reciprocal of this constant of proportionality is defined as the absolute temperature. The reciprocal of the constant of proportionality of the constant of proportionality is the absolute scale temperature. So, you see that it defines the absolute scale temperature also, and mathematically this is written as that change in entropy delta S is delta Q by T heat added reversibly. And in general, where the greater than sign implies irreversibly and equal to is for when heat added reversibly. These are also possible to get from those Kelvin Planck statement or Clausius-Clapeyron statement. Now, this also has another significance. It also says that it also implies that work can be converted completely to heat, but heat cannot be converted completely to work, or heat is a degraded form of energy. That is, this also implies, this has an implication that work can be completely converted to heat, but heat cannot be completely converted to work. Meaning heat is a degraded form of the energy. So, you see that the second law gives us various possibilities, that if a process is adiabatic and reversible, then there will be no change in entropy. That is, adiabatic reversible changes are isentropic change. In any other reversible change, the change in entropy will be proportional to the heat added. In other, if the change is irreversible, then the relationship will change to this form. That is, delta q will be less than T times delta S, but for reversible case delta q will be T times delta S. Now, particularly we will be interested in that reversible adiabatic or isentropic processes, and a second law, consequence of second law, that in adiabatic reversible change entropy will remain constant, will not change, and in adiabatic second reversible change the entropy cannot diminish, the entropy will increase. Now, let us consider a small reversible change. Now, let us consider a small reversible change. Consider a small reversible change where work is done by compression. On the system in our case we will always consider fluid. By compression only. Since we are considering our small reversible change, then delta q is T delta S. Hence, that first law delta q is T delta S, that equal to delta E plus P delta V. So, this is a combined form of first and second law. So, combined form second law. Now, in this equation all the variables are state variables, all these variables are state variables, and hence this relation must be valid for any infinitesimal transition in which work is done by compression, whether reversible or not. So, all are state function, contains only equation contains only state function, equation contains only state function, and holds for any small change. Reversible or not. Okay. The only restriction is that the work must be compression work. It is not valid for any other type of work done on the system. Now, of course, if the process is not irreversible, that is that equation holds, as we mentioned, that even if the change is not reversible, another way that this equation will hold even if the change is not reversible, but if the change is not reversible, then this is not the heat and this is not the work. That is that is the relation holds for irreversible process also, but then and that is these are not true, the heat added is not T delta S, the work done is not minus P delta V, but the total change, that is T delta S, is equal to delta E plus P delta V, still holds. We will now define few more important state variables or state functions, and one very important state function, let us say few more important state functions. Enthalpy. Enthalpy is also again an extensive property. So, we have a specific enthalpy, which is the intensive property and enthalpy per unit mass. See, this enthalpy per unit mass we will denote it by H. Okay, since here we are defining all capital letters, let us use letter. So, this H is defined as E plus P v, which gives in the differential form d H is d E plus P d v plus V d P, and we have already seen that d E plus P d v is T d S. So, that is and this implies that for a small reversible change at constant pressure, d H equal to T d S is equal to d Q. And since it is reversible, T d S is and this implies that the enthalpy basically represents the total heat content of the system. And also if we look to this equation, this also involves only state variables and hence apply for both reversible and irreversible changes. One more important state function is Helmholtz free energy. And this per unit mass we define this by say F and the definition of this F is E minus T s. So, this gives d F equal to d E minus minus d E minus T delta S is P d V minus So, again in a reversible small change at constant temperature, dF equal to minus P dV or equal to the compression work or useful work. So, in a small reversible change, at constant T, so, you see that if we have an isothermal small change or isothermal small reversible change, then the gain in free energy is work done by the work done on the system. So, work done on the system in a reversible manner at constant temperature is actually the gain in free energy or Helmholtz free energy of the system, and thus the Helmholtz free energy is related to useful work. The other free energy function is called Gibbs free energy. This is once again another extensive property. This is also an extensive property like Helmholtz free energy, enthalpy or entropy. And Gibbs free energy per unit mass G is defined as E plus P v minus T s, or you can write H minus T s. And hence you can write d g equal to d h minus T d s minus S d t, and from the definition of enthalpy d h minus T d s becomes V d p minus S d t. And this Gibbs free energy also is associated with or the available work output. Now, with this now we will try to derive few more important relationship. First of all, let us consider that will be using say V and S as the two independent variables. We have already stated that for any pure substance, any two state variables can be considered as independent variables, and all other state variables or state functions can be obtained in terms of those two. Earlier we expressed pressure and specific volume as two such independent variables and express all other as a function of pressure and volume. But now let us take V and S are the two independent variables, and hence all other can be expressed as functions of V and S. All other state variables can be expressed as functions of V and S. And this already we have. Sorry. Now, this implies that we have d E d V at constant entropy equal to minus P. And also d E d S at constant volume equal to T. So, we have obtained new definitions of pressure and temperature. Now, we can evaluate the second derivative of we can differentiate the first relation, that is d E d V at constant entropy as minus P. So, we differentiate it again with entropy now. So, this makes similarly, we have d E d S at constant volume is T. Now, we differentiate this again with V at constant entropy, and that gives us and combining these, this gives us dP ds V as minus dt dV s. This is one of the Maxwell's law. Now, also from here this dt dV s can be written as dt dP at constant entropy into dP dV at constant entropy. Similarly, we have dP ds at constant volume is minus dP dV s into dV ds P. And this becomes minus dt dV s. This is a thermodynamic identity. Now, we can mark this first equation as A and this as B. And combining we get dV ds at pressure is dt dP at s. This is also another Maxwell law. This relation can also be obtained in an another manner, that is, we could have defined second derivative of h in two different manner, as we have done here for second derivative of E in two different manner. Similarly, we can define second derivative of h in two different manners, second derivative of f and g also in two different manners, and get total 4 relations, and all these 4 relations are called the Maxwell's relations. So, we have 4 Maxwell's relations or 4 Maxwell equations. We have dP ds at constant volume is minus dt dV at constant entropy. We have dV ds at constant pressure equal to dt dP at constant entropy. dV dt at constant pressure will do minus ds dP at constant temperature, and the last one dP dt at constant volume is these are these four relations are known as Maxwell's relations, and they are quite useful in many thermodynamical relationship, and at least in one or two cases we will use them. So, what we have done today, first we have discussed about second law and the concept of entropy and the absolute scale of temperature, and based on that we have subsequently defined few more important thermodynamical state functions, enthalpy, Gibbs free energy and Helmholtz free energy, and finally we have obtained the Maxwell's equations. So, further useful relations that are often used in high speed aerodynamics will derive subsequently in our next class.